We'll now come to several more aspects of the tetrahedron, and then I'm going to have a break, but I'd like to wind this part up. I'm going to have a set of cheese platonic solids. There's a platonic cheese cube and octahedron, tetrahedron, icosahedron, the whole family. And going to take the cube and slice parallel to one of its faces. What's left over is no longer a cube. So I take the dodecahedron and slice parallel to those X faces, no longer a dodec. Each one of them becomes asymmetric, with one exception, the cheese tetrahedron. So I slice parallel to one of its faces. There's a little smaller tetrahedron, but absolutely regular. So I slice parallel to the second face. Gets so small still, absolutely regular. Try the third face, fourth face. Always just so small, but always regular. Tetrahedron, then, is the only symmetrical polyhedron, which is not, whose integrity of symmetry is not violated by accommodating local aberrations. This has a very, very extraordinary important property. And it is inherently four planes. It's not a three-plane system as we have with the X, Y, Z coordinate system. It's inherently a four-dimensional phenomenon. Now I find then the tetrahedron, when I move one of its faces towards its opposite vertex, we say it gets smaller. As it gets smaller, its lines shrink at a velocity, arithmetical velocity, arithmetical rate. The areas shrink at an area of the second velocity of the second power, and the volume gets smaller at the velocity of the third power. Three completely different rates. But as it gets smaller, there's always four vertexes, there are always six edges, there are always all 60-degree angles. These are absolute constants, have nothing to do with size. So I have then this conceptuality independent of size that's absolutely independent of these three different velocities.